Welcome to this tutorial on how to build a fractal task. In this video, I'll walk you through all of the steps involved in building your own Python function that can process an OMSR and add it to a fractal server. We'll go through the 5 steps you will need to go from the task template to a task that can locally process an OMSR file to something that you can add to an existing fractal server instance to run your task. First, you'll of course need some example data, like the OMSR example provided in the link in the description, which contains a 2D and 3D OMSR file of fairly small images, just 2 images of nuclei, and we'll use those to show how we can build a task. So your go-to when building a fractal task is the repository called the Fractal Task Template. Again, the link will be in the description of this video. And using this task template, you can get the whole setup for a repository to put your own task in to package it up nicely. The way you use this is you first install the copier package in an environment. You can install this in your own Conda environment, use pipx, however you like best. And then you use copier to create your own version of this package. So let's create a fractal demo, fractal tasks demo package. And copier will guide us through the process, asking us a few questions of how we need to set up this repository. So provide your name, give it an email address, a name of your project. So we called ours Fractal Tasks Demo. If you have a homepage to point to where you want to link users to for documentation, you could add it here. And you can give a short description of your package. Demo fractal task for thresholding. The package is called Fractal Task Demo. You will also see it here in the folder that you were. This package will contain some of the helping parts around, packaging this up as a Python project, for example, a project.toml file, and it will contain some of the dev tooling you'll need to build up tasks once you have them, as well as a little example task for some processing. So what we'll do now is build up on this example task to have our own task, and the goal of this task is to find some thresholding so that we find labels, something like this, based on the user-defined threshold. So for this, we have our fractal demos, or fractal task demo repo. We initialize it in this repo so we can do some version tracking. We add all of the existing template files to make an initial commit. We could now create a GitHub repository and then upload it there to track it further. But for this local demonstration, let's just start developing. The package comes with another README that describes how you should be going through developing the demo package. First part you'll want to do is set up some environment to work in. I'll create a little Conda environment for this. In some recent Python version. This will set up our own little virtual environment that we can work on isolated and don't mess with any of our other Python installations. In this environment, you'll want to install all of the dependencies that you'll need for your package. And the dependencies are 3. And for this package that we're building, we'll need to add a scikit image dependency. This is set. We can pip install -e all of these dependencies. This will then install all the dependencies we need, in this case the core part of Fractal Task Core, as well as scikit image. will install the package for you locally. Now, once we have this package installed, we can start actually developing our processing task. And we have a template for how this is structured in your demo or your template repository. It's in source, the name of your repository, and here's a basic thresholding task. And we'll want to modify this, but what it basically does is it's a Python function that takes a SAR URL and any parameter that we specify, and does some stuff, and is being run with a main function that uses the run fractal task utils from the fractal task core package to run your function. We name our function, we name the file that we put our function in the same as we name the actual function. So let's make a copy of this thresholding task and call it thresholding label task. And this is what we'll be building up towards. So I picked up some of the different imports we'll need for the tasks that we're going to build. Feel free to look through them afterwards to import some of the dependencies. And what we'll now do is we'll make a task called fractal, a thresholding label task. And we'll make sure that this is what's being run by the main function. And this task should do some stuff. Maybe in its easiest form, it needs to have a few parameters. It needs a SAR URL. It needs a threshold, which will be an integer. It needs a channel. For channel, we have a channel input model that we provide, which is one of the imports here, which allows Fractal Web to nicely read in your channels. We want to have a label name optionally where a user could define how the resulting label should be called. If they provide one, it's a string, but they're not required to provide one. And we may need other parameters later, like the min size of objects that we filter. This is an integer, or whether we want to overwrite existing labels. You will notice that I am typing all of the parameters that we're using here, and we're using Pydantic's validated arguments for this function. The reason for this is so that we can build schemas to show your Python function arguments nicely in Fractal Web and validate that your function is actually getting the correct measurements. Now, we'll also want to have a docstring that fully describes what these different parts do. For this docstring, I prepared a short version that says that we're building a thresholding function, and it defines what all of our parameters are doing. Now, once we start the task, we get the SAR URL, so we might want to log so our users know what we're actually working on, and then we might want to load the metadata of the SAR URL into this ngFF image meta object and print some log information, some of which may be relevant, for example, what the full resolution of our image is. Some of it might be less relevant for us, as in getting the coarsening factors between the pyramid levels. Once we have this, what we'll also want to do is get, based on this channel input, figure out which of the channels we actually want to load. And for this, we provide a helper function called getChannel from ImageSAR. This takes 3 parameters: the actual ImageSAR path, which is just our SAR URL that we provide as input. Second, it takes a wavelength ID, and that's one way you can specify a channel. And the channel object provides a wavelength ID if this one is set, or is none if it's not set. And the other way to specify a channel would be a label, and that's also something our channel model provides if the user sets it. This then gets us a little channel model which is of type Omero channel, that we can deal with. Data about our channel, we might also want to prepare how the label name would be set, or handle the case when a user doesn't set one. So if the user didn't specify a label name, we could come up with some of our own label name definition. For example, we could name it based on the label that our channel object has, and depends on something like thresholded. Which means we're ready to load the array. For the moment, I'll delete all the parts we'll do after loading the array. So we'd have the initial half of our task of parsing the input and then loading from Dask based on our star URL from the full resolution of our image an array lazily, and logging some info about it. Now, before we dive into its actual processing, let's set up some local script so we can test how this task is running on some local data and do some interactive development with it. So we do some local script that we call example run.py, and for this what we'll want to do is we want to import our task. So our package is called Fractal tasks demo, and I need to actually be in the correct Python interpreter here. It's this one, and we have a threshold label task, and this one we import. So this is a task we'll want to test. We'll also need to have our channel model, which we import from Fractal task core channels to provide input as if they were coming from the web interface. And then we want to define what our threshold labeling task will need. What it will certainly need is a star URL. So we'll need to define this. What we also need to define is a threshold. And last but not least, what we need to define for this task is the actual channel that we're using to threshold. So 3 variables that we need to set. The star URL is a string which points to the location of the actual OMSR image. For this purpose, I have an example OMSR file that we can be processing on my desktop here. This is a plate OMSR file. We want to be providing the path to the actual OMSR image, which is the star structure that contains the set attribute with the multi-scales metadata. So we get a path to that one. As a star URL, we define a threshold. Let's say it's about 200, and we want to define a channel. Our channel is a channel input model based on channel input model, and we can either define a wavelength or a label. Let's use it with label, and I know that I have a channel in here that is called DAPI because it does show up like this when I drag and drop this into an API viewer. So that allows us to run our task. We should see, if we run this task, some logging info about our array. So let's see if the first part of our task can successfully run. So this task now goes. It will get the star URL to know where the star file is, load some metadata, load the channels, and then lazily load the array. And we see that we have some array loaded. It's a bit wider than high. It has 2 set planes, as we see over here. So we know we have an image to deal with. This image is loaded as a Dask array, so it's not actually loaded in memory right away, but we can now apply some processing. And for processing, let's define a process function, and this process function should provide a label image. So our processed result should be some label image that will be created by a function we need to define that processes an image. And for that function, we will pass our actual array and we'll call compute on it to just create a NumPy image. This will work fine in this way for small images. If we have huge 3D arrays, we probably wouldn't want to process our whole array at once in this way, because now everything gets loaded into memory, so that can be somewhat inefficient. In our case, our process function will also need to know our threshold, and our function probably will also want to know our min size if we do any filtering out of very small objects. I prepared an example process function, so we don't need to go through writing all of this together now. My little example process function will take these inputs, it will apply a threshold, remove some small objects given by our min size filter, perform morphological closing or opening and dilation, so we remove some holes, and then apply a label to the image so that every nucleus, at least every non-touching nucleus, gets a unique label. So we could run this, and then maybe we want to print the shape of our image, maybe also its type. Something failed. And debug locally. Now, if we look more carefully, we notice that our image actually had a 4D shape, dimensions channel CYX. We probably don't want to process the image as a 4D image. We just want to process our channel of interest. So we need to be a bit more careful when we're loading the data from SAR. So what we can do is select a given channel, and we defined our channel model above, and from this we can get the index of our channel of interest. So now we should get an array that is of shape ZYX, and our processing should hopefully work. Now we get NumPy array of the expected shape being processed. Good. All that remains to make this into a function that we could really use is actually doing something with the label image now. So in this case, we want to save the label image back to the UMSR, and I generated a few helper functions that will help us do this, that I'll add to the script now. First one here, which is a helper function that will generate the C attributes that our label image needs, which will be useful because then what we do in the task is we first use this helper function to generate the necessary attributes. We then use a little helper function we defined in Fractal task core, which prepares a label group for us and adds the right attributes and handles overwriting of this group, these kind of things. And in this new label group, we can actually write the SAR image. If we want to write the SAR image, we need to correctly have our variables named. This creates a data set at 0, so at full resolution of our label image in the SAR file. And then last but not least, because we want this to be pyramidal, we'll add a function to build pyramids on our given SAR image. So again, let's run this function locally and see what it produces. It does run through. Now if we look on our desktop, we now have a labels folder with labels created. So if we add this image freshly to Nempari, we should see that we have both the image as before, but also our new thresholding segmentation, which clearly is heavily over-segmented or under-split. Good. Now, for the sake of this demonstration, let's assume this is the kind of thresholding and labeling that we want, which means we have a Python function here that takes in SAR URL and whatever parameters we want. It's using the validate arguments Pydantic decorator, and it has a doc string that describes what its inputs are. Within this function, it loads data from an OME SAR, specifically here, and it writes data back to a SAR. So this is all we need to have a fractal task. Now step 3 of building a fractal task, that is also described in this README here, is actually adding it to our image, to our task list, so that we tell Fractal that the code in this function will actually be used to build a task. Now, in your demo repo, what you will find is in the dev package a so-called task list. So we can open this in code, and you will see currently this holds one task, this thresholding task that was already there as an example. Let's add a second task. And this task is our thresholding label task, and it's defined in the thresholding label task.py function that we just created. We can give this task specific meta parameters, as in define how many CPUs it should request if it runs in a Selenium cluster, how much memory, and many things more. If you want to learn more about what you can do with tasks, have a look at the Fractal page and the V2 task documentation. We have in-depth documentation here about the different type of tasks, parallel tasks, non-parallel tasks, and compound tasks, their input API, as well as how they can provide outputs like updates to the image lists back to Fractal. For our simple thresholding task, this is all we need. So we gave all of the information to the task list. What we now need to do is build the manifest, and there's a manifest defined in this little create manifest helper script, manifest building. So we call this, we go to in this terminal, over here. Now this goes through all of the parts in task list, and it creates an actual manifest entry, which is a JSON file that now says it has info about a thresholding task and a thresholding label task. And for our thresholding label task, all of the descriptions we made, for example, about what the minimum size is meant to be, is filled in the manifest. So that means we have a manifest. We could add this to a repository, of course. You could also define so-called non-parallel tasks, so tasks that are meant to run on all of your SAR files, not just on a single one, or compound tasks that handle more complex cases. I'd refer you to this documentation on task types for this. Now, we could, of course, now work on good testing to make sure our tasks are tested, and then put them on a GitHub repository and even publish them to PyPy so that everyone can install it very easily. Sometimes in local development, the easiest thing to do is just generate a local build of the package though. So we can call python-m build after we've installed build in our environment. And this will create a little wheel file, which is the same that PyPy would give you. And this wheel file we can pass to Fractal server, so that the Fractal server can install those tasks and set up its own little environment with them. So now we have a wheel file in this dist folder here, and we can go to a running Fractal server instance, for example, one I'm running locally, go to tasks, and either install task package from PyPy or now get it from the local part. It's in this dist folder, and the file we want to pass is the one that ends in .wheel. And we tell Fractal to collect the tasks in this package. So it installed the Fractal Task core task before, now it's installing the Fractal Task demo. What it's actually doing is setting up its own little Python environment and installing all the dependencies we've defined in there. And then it's taking note of where our executables are so it can run this Fractal task on any SAR URLs you tell it to. While we wait for the installation, I have already prepared in our project page an example project, a little demo workflow for this. And this demo workflow consists of running a conversion to an OMSR file, then running self-pose, and once our task is installed, it will show up here in the selection. Actually, installation must have finished. So now we have the two tasks in our package, and we add our thresholding label task. We could have different versions if we version tag our tasks and install them separately. And we add it to the workflow. So now this workflow consists of a first step to convert the data to OMSR, a self-pose segmentation, and a thresholding-based segmentation. For this thresholding-based segmentation, we have two required arguments, the threshold value, let's try something slightly lower, and our channel argument. Now, this comes with description of what we want to do, and we can choose which one of these parameters we want to use. Let's say we want to specify as DAPI. We could give this a name, something like DAPI thresholded, and change the min size filter and change other options we set in the task. Once we're happy with all the options we've set, we can run our workflow. This workflow gets run locally, and once this is through, it generates a new OMSR file, I think on my desktop, that will have the results of this processing. Let's have a quick look. On where I place this. The demo dataset. Yes, on a desktop in the folder called demo. It creates an OMSR file here with some images. And if we go check on the workflow, it has finished the conversion and currently running self-pose. Once this is finished, it will run the thresholding task. While we wait for this to briefly review what did we learn today, if you want to build your own fractal task, there are 5 main steps to this. Step number 1 is use the fractal task template to have a repository to put your task in with all of the little helper functionality for building manifests and some templates. Step number 2 is actually develop your Python code locally to process an OMSR. I really recommend also testing this locally to see what is happening and whether you get the desired outcome. Step number 3 is adding your task to the task list in your repository. And then you package your task locally or by adding it to PyPy, and you install it on a given Fractal server. And then of course you run it, and this task is now run through. We can compare the result and have a look. We get some labels provided by self-pose and some slightly worse labels provided by our thresholding. That's it. Have a good day.